We are live. Hi everyone, thanks for joining and welcome to day two of our workshop. I'm very excited and feel fortunate that Pedro has agreed to give a guest presentation and being a guest lecturer for this workshop. He has done amazing work in AI for architectural use cases. I have personally read like most of his research papers, and they're very cutting edge in the way a human can work with agents to do spatial design. And I find a lot of inspiration from his work. uh, Earlier, like a couple of months back, we also reviewed a few of his papers, and I got a chance to interview him for my podcast. If I highly recommend you guys to check out Cradle Group, CRAIDL, where Pedro and other of his PhD colleagues have formed a research group which is focused on AI in architecture research work. And I look forward to this presentation. And Pedro, the stage is yours.
Thanks, Mayur. Thanks for the invitation. Hi, everyone. Hi, everyone that's here in the room with us. Hi, everyone that's watching. And I'm going to share my screen, and I'm going to, one second. I think you can see my screen now. Um, so today, I'm going to talk about generative design and applications with artificial intelligence. And I'll provide like a brief introduction to some concepts like generative systems, generative design, maybe a little bit of machine learning, but mostly I want to talk about this concept so we can discuss. I can share some 2 or 3 projects that I worked in the last years, and I think it's nice because a lot of the things I'm going to present today, they're connected to the activities you're going to be doing in this workshop. So this, I think this is a great opportunity to have designers talking about AI and machine learning. So quick bio here. I'm an architect and urbanist. I'm a computational designer. I'm an educator and a researcher. I have a Bachelor of Architecture and Urbanism from the University of Brasilia, Master of Science from the University of São Paulo, and I'm currently a PhD candidate in computational design at Carnegie Mellon University. Mayur mentioned Cradle. This is the group, Cradle. We started last summer. Basically, we are all PhD students, PhD candidates from the computational design program. I'm Pedro Veloso, Ardavan Pitcoli, Jim Marie, and Manuel Guevara. We are all like designers, architects that we went to CMU to do our research, and we ended up like learning about machine learning, deep learning, and each one of us has a different expertise, interest. Sometimes there are more overlappings or less, but overall, like we have expertise in natural language processing, reinforcement learning, and deep learning in general. And for those who are interested in our work, please check the website. It's here. There are papers, there are like some descriptions of projects, and so on. With this short bio and introduction, I'll start talking about generative design. That's the first topic of this presentation. And let me know if maybe I'm saying something that's too obvious. Maybe generative design is very obvious today. Everyone knows what does it mean. But in any case, I'd like to make sure that everyone's on the same on track here. So I'll provide a brief definition. So conventionally, especially for those who who are older, when you learn architecture, when you learn like even other schools of design, the way you design, well, is by interacting with. I probably have like problems with my slideshow here. Play narrations, use timings. Just a second. Transitions. Yeah, no transitions. Okay. I'll just add more. Okay, that's fine. But basically, the idea is that when you when you design before you're talking about generative design, conventionally designers, they use some form of representation. If you think about like architects, they use like sketches, models, and it's represented here as this like representation, abstract representation of a chair. And they use those representations, they change those representations, they iterate, and they learn with those representations, and they end up like developing a design by refining those representations. So there can be groups of architects working the same representation or different representation. But these days, there are other ways of designing, right? Like we have many other resources. And especially using computers, one thing we can do is instead of like designing directly into our like design representation, instead of like sketching our final product and starting to develop it, we can kind of like externalize the logic of the design. So the idea of generative system is that instead of creating the design directly, you take that logic of design and you create like a kind of like a model that can generate those designs. So here you have a group of designers. They create like this kind of like this machine that has a generator, has an input and has an output. And depending on how you create that machine, you can generate like a different set of design alternatives. So in this case, I'm representing as chairs. You can create a certain generative system or generative model that can generate like a variation of chairs. And after that, you can interact with that model just by like changing the input of that generative system, seeing the output. Maybe it outputs one chair, maybe it outputs like a catalog of chairs. Maybe it uses an optimization and tries to maximize some of the characteristics of the chair. So this is like the basic notion of generative systems. So you create like a model that helps you to design something. So it's kind of like an indirect form of design. And this is like just to move from like more of the theory to like to the industry. There are like, I think this is less in these last like years. This is a topic that has been like trendy in the industry. So this was mostly in academia in the past decades, but recently it became like a topic that has been discussed in the industry. So here are some examples, like SpaceMaker. They're developing kind of like a software for decision making with environmental analysis, generation of urban blocks, and so on. This is an example from Autodesk of an office that was generated using optimization. TestFit creates like more like uses more like standard types of designs to try to evaluate the feasibility, to evaluate like different alternatives of design. And also, you probably know about Finch 3D. There are like many videos showing like parametric models for different design problems. So this is, I just want to show this slide that generative systems and also artificial intelligence, that's also part of these ideas that are used in generative systems. These are not like only buzzwords, but these are also things that are happening in the industry in terms of automation, design customization, and informed decision making. And this discussion has been into the media too. Like we had in the past, this is a book from 77 that discussed the automated architect. But now in the last years, 2015, 18, 19, you have examples from articles discussing this idea of automation in the field of architecture. Sometimes that you have that fear of like the profession being automated and losing part of its job. But others are more positive and showing that actually we are redefining the role of designers, and that's going to improve the quality of architectural design. And generative systems are really they're hard to teach if you think about architecture education, because there's so many topics when you're going to talk about AI, generative systems. There's so many topics included in generative systems, so many different knowledge from different areas. And here's just a diagram showing that you have like since the classic artificial intelligence techniques from the 60s, 70s, to techniques from simulation, from physics, agent-based modeling, and recently machine learning. So you have all these things together that we are accumulating and we are using to create our generative system. And as a way, to make it more accessible in terms of like education and in terms of research. Recently, I worked with Professor Ramesh Krishnamurti on a taxonomy. This is just like a brief presentation of this taxonomy. This is a taxonomy that tries to show like the different pieces of generative systems. So if you want to create a generative system for part of your building or part of your design, this taxonomy can help you identify aspects that, let's say, parts of the generative systems that you can incorporate. For example, some of them, like parametric modeling, probably optimization, rule-based modeling. And if you're interested in knowing more about this taxonomy, it's available in the Routledge Companion to Artificial Intelligence in Architecture. But today, I don't want to talk too much about this taxonomy. I'll let you explore if you're interested in. I just want you to focus on this last row of this taxonomy. This is something that was added recently to our generative system. So in the past, we would create our generative systems using rules, parametric models, and so on. And now we have resources to use machine learning, to use learning to create generative systems. And I think there's a huge potential to develop like different generative systems for our design practice. And before I continue here, maybe just to have some feedback, how many of you are familiar? How many of you are familiar with machine learning? Is there any one of you that machine learning is something new for you, or machine learning is like common sense for everyone at this point?
If you want to raise hands or comment.
Okay. I mean, uh, let's see the comments. Okay, it's new. Nice, relatively new. Yeah, machine learning. I mean, it became in the last like machine learning has been part of AI for decades, but recently with deep learning became like in the last like 10 years became like a really important topic. So I'll provide a brief definition of machine learning here. And the reason I'm doing this is because I want to explain some of 2 or 3 projects, and it's important to know these ideas. So machine learning, the basic idea of machine learning is that instead of specifying a program to solve a task, so let's say let's think of designers here. You say, well, I want to create a program that generates a chair, right? Okay, some people have experience, that's good. So instead of creating that program, instead of going there coding, programming, and say, okay, I'm going to generate the chair using this parametric model, or maybe I'll create certain logic and I'll use scripting and I'll generate like a catalog of chairs. Instead of doing that, machine learning allows you to train a computer to learn how to solve it. So instead of you creating the logic to generate the chair, you're going to use maybe data or maybe simulations. You're going to extract data from simulations, and you're going to train a computer to solve that problem. You're going to train a computer to generate chairs for you. So it's a very powerful concept, because as a designer, you take one step back, and instead of trying to code everything by yourself, you start to be the person kind of doing the meta design. You say, okay, I want to generate this type of chairs. Maybe you have a data set, and I'm going to train a computer to generate chairs that they look like chairs inside that data set. So that's a basic definition of machine learning. And as you can see here, there are many areas. So in general, people define like 3 branches of machine learning: unsupervised learning, supervised learning, and reinforcement learning. I'm not going to talk about all of them. I'll focus maybe on 1 or 2. And one element here that's really important is generative modeling, that typically is placed close to unsupervised learning. And the idea is that you can create models, computational models that, in technical terms, they learn the distribution of a certain data set. They learn how to describe how a data set is generated. So the idea is that you use a data set of chairs, for example, to train a model, but that model not only learns how to do, for example, classification or something that a task like classification, but it learns how to generate new, let's say, new samples, new alternatives of chairs based on that distribution. And there are many examples like PCA, autoencoder, GANs, and I think the models you're using in this workshop, probably some of them are inside this category. And another concept that's important is deep learning. So we've been talking about machine learning, but most of the discussions about machine learning, generative design with machine learning these days, they rely on deep learning. And the idea of deep learning is that you have a computational model that learns complicated concepts by building them from simple ones. So it's able to create like a hierarchy of concepts and is able to use those representations to solve a certain task. So here is like a diagram that I created based on a famous model in machine learning that's called VGG16. And it's basically a model that uses convolutions. So I don't want to get too much on the technical side, but I just want to show that it's a model that takes as an input an image, maybe has like 3 channels with colors, and is able to break that image into certain like features. It's able to break into certain, to use that image to learn certain representations. And as you generate diagrams, for example, here I'm using an optimization to try to visualize certain parts of this network. And you can see that certain parts of the network learn abstract concepts, right? Maybe one part learns vertical lines, another one learns like a certain type of curve, maybe something that looks like an eye, right? So the network hierarchically breaks the idea of an image into different concepts. So that's why, in this case, neural networks are really powerful because they enable you to learn features so you can solve the task that you're interested in. And here's just an example. I'm taking an image. This is the Cathedral of Brasilia. It's a building by Oscar Niemeyer. And I'm using a technique that's called I think it's deep dream. So I'm basically hallucinating. You can see that some patterns that are learned by the neural networks start to be part of the image. So you use a technique to start to incorporate those patterns. It starts to change the original image and to incorporate some of those patterns. And down here, I think is a technique you've been discussing. I'm doing a little bit of style transfer. So I have an image with a certain style, that's the image P, and I have the image of the cathedral, and I'm applying that style to this image. And as you can see, step by step, the characteristics of this image on the left start to be incorporated to the image of the cathedral. This is just to show that you can do a lot of things with neural networks, with these models. They're really powerful. So just this is my last theoretical slide, and then I'll show some projects. Yeah, that's correct. So basically what I want to show here, I think, I don't want to be very technical about deep learning, machine learning, and all that. I want you to have like a clear concept about generative systems, generative design. So the idea is that instead of like programming your own generative model, going there and coding how your generative model is going to create chairs, for example, instead of doing that, like you have here in B and C, you can use something like a data set. You can use some source of knowledge about that object that you want to create. So imagine like how many chairs were created at this point. So you can use that knowledge, and you can tell your model, for example, your network, and you can train it with those chairs, that data set of chairs. You can train that neural network to do something. Maybe generate the chair. Maybe do style transfer. Maybe combine the chair with another object. But you learn something from this data set. So your generative model here uses that knowledge, uses probably a neural network to help you generate new chairs. So that's the message that I have here at this point. So now we can do these generative systems or generative models that they learn from data and experience, and that's very powerful. So I think in this workshop, when you're playing with these models, start thinking about what are the tasks, what are the parts of design in your own practice that you could use a data set, you could use like a neural network to help you uh, design. So okay, this is the end of like more of the conceptual theoretical part, and I'm going to show 2 or 3 projects briefly here. And the first one is called Deepcloud. This is a project, probably the first full project that I developed uh, in terms of like deep learning. I had like small projects before, but this is one that I actually developed and was part of an exhibition. This was developed by Ardavan Vitukoli and me when in 2018. This was a collaboration, and our idea was to explore this notion of co-creation with artificial intelligence. And this project was published in Acadia. It was exhibited at CMU, NeurIPS, and there's some references here for those who are interested. I can provide that later. But the basic idea is that there was a model at the point that was published that was developed by Acleoptas, and that was a model that was able to reconstruct point clouds. So I'll talk a little bit about the technical side here, but I'll try to keep track of the task that's being addressed here. So imagine that you have a model here. Forget for now that you have layers, you have like operations, you have a lot of things happening here in this part here. This is a model that's called an autoencoder. So the idea is that it takes a representation, can be in this case a representation of a point cloud, but it could be voxel, meshes, could be text, could be anything, and it compresses that representation. So you can see here, you take this point cloud, it does like a series of operations and compress that. And in this case, it's in a vector of like few numbers. Maybe it's a vector of 6, in this case, it's 32, but could be 16 or more. So in this case, you have like a point cloud with more than 2,000 points, and each point has 3 coordinates, and you're compressing to 32 numbers. So you're basically learning how to compress that. And then that's the encoder. And you have a second part that learns how to decode that and reconstruct the point cloud. So basically, you're training these 2 parts of a neural network to, one, to compress to a vector that represents this latent space. And then another part of this neural network is reading those 32 numbers and say, okay, if you give me these 32 numbers, what am I supposed to build? It tries to reconstruct that point cloud. So what's nice about this is that after training this type of model, we can eliminate this first part of the encoder. Okay, so eliminate this first part here, and look what you have. You have a model that the input is like a vector of 32 numbers, and is able to generate point clouds for you. So it's more like, for those who are familiar with Grasshopper, imagine instead of you going there and creating a Grasshopper model to generate chairs, now you have a model that it learns how to generate point clouds of chairs. And now you just need to pass numbers to this vector here, and it's going to generate different chairs. That's the idea. This is the first part of Deepcloud. When we started playing with this model, we trained the model, and you're thinking about how can you interact with this model. So we have, I'm sure, oh, okay, here we have on the, oh, here we go. On the left, we are playing with like Galapagos, just using a genetic algorithm and playing with that latent space and exploring like chairs inside that space, the latent space. So you can see that it starts to learn like about like point clouds that they look like different chairs. So we didn't have to model these chairs. We learned from data. And here on the right, I'm using like leap motion and playing with that vector to explore like, oh, how can I add it to my chair with like hand gestures? But that's a little bit tricky. So we moved on, and we actually use, instead of using that type of interaction, we used a mixer, as you can see here. We used a mixer. We created like an interface using like a Django, JavaScript, and we created an interface where you can interact with the decoder using a mixer or using the mouse. And this is the first time the project was exhibited. So we had like this screen, and we had the mixer and the mouse here, and you could interact. Here's in detail. And we also printed some of the chairs or objects generated there. And here's like what you see on our screen, right? You can see like we created a menu, and each of these sliders here represent like one of the numbers of that vector. And as you change those numbers, you get like different chairs. So maybe one slider you change, a certain characteristic of the chair changes. Another slider you change, maybe the chair gets larger. And as you play with these sliders, in that case was analogically like with the mixer, you explore like different chairs. And again, we never created a model to create that chair. We learned that model. Second project, I think I still have some minutes. It's called Synthesizing Urban Structure. This is a project that was developed by Marie in 2019 in a course that I taught that was called Generative Systems for Design. And then we collaborated and we published in Cadria. So the basic idea here is that we created a data set from Carnegie Mellon is in Pittsburgh, in Pennsylvania. We created a data set of aerial views of kind of like diagrams of urban fabric from Pittsburgh. And we used those diagrams, as you can see here on the right, these are more or less how these diagrams look like. And we used those diagrams to learn how to generate urban fabric based on the characteristics of Pittsburgh. So we used a model called WGAN, and basically we passed like more than 40,000 images of with those diagrams. And the WGAN model learned how to generate new diagrams similar to the ones in the data set. And then that diagram is translated to 3D. And here's like one of the videos showing the interface. Again, you can play with these sliders, and the model generates different like urban fabric diagrams there. So basically play with that again, but the tricky part here is that you don't know what the sliders are going to do, right? So you're basically like playing with this black box and changing the sliders and figure out like new urban diagrams. And after that, you can translate that to Grasshopper. Let me see if yeah, so you can translate that to like a 3D model using computer vision. And here's an image playing with the parameter space of the trained model, as you can see here. And here's an experiment just tiling a urban space using the characteristics from downtown, but occupying the tiles in a more like residential area in Pittsburgh. So we are playing with different like morphologies and just exploring the potential of that model to generate like different urban space. Very speculative. This is not a design tool. It's more like a speculation at this point about the use of GANs for design. And here you can see the results. All right, so Mayur, I can stop now, or I can show one more project. Let me know how is the time going.
Please go ahead. Yeah, no problem.
Okay. So I'm going to show a last project here that's related to my PhD research. So the previous projects, they were mostly related to generative modeling. So that concept that I described earlier. And this one is related to reinforcement learning. Briefly here, for those who are not following the advancements in reinforcement learning, here are some examples of research work in reinforcement learning. You have reinforcement learning has been used for learning how to play games, like board games, like Go, and other board games. And recently was able to beat like the world champions of Go. So that was a huge achievement for AI. It's also related to robotics. So with tasks that you use, like robotic arms. These are tasks that you can use reinforcement learning for training. In the column at the middle here, you can see reinforcement learning being used to discover behaviors. Like you have an environment, like with like a physics engine, and you have a humanoid trying to, maybe in that case, run and get to a certain point, or maybe at the bottom there are two humanoids like fighting, and you use reinforcement learning to learn behaviors that can solve a certain task. And on the right here, you also have reinforcement learning for video games, in this case for StarCraft. And here at the bottom, you have like one example that was really famous, hide and seek, where OpenAI used reinforcement learning for multi-agents to play this game where some agents try to hide, some agents try to seek the other agents. And they discovered that over the time, there are like emergent behaviors as you keep training these two groups of agents. So basically, this maybe is a little bit more technical, but I just want you to focus here on the image. The basic idea of reinforcement learning is that you're training an agent to, here's the agent, you're training an agent to perceive an observation. So it understands the road, and it has a program that it perceives the road and looks at that observation and takes an action. So if you think of, about a robot, for example, a robot might have a camera, it perceives the scene, maybe has information about the joints, and it perceives the scene, and it knows what actions to take to try to achieve a certain goal, maybe to grab an object, right? So it knows, okay, at this point, the object's there, I should move here. So, and as the agent takes that action, it changes the environment that's represented here as this role. So you have an agent and have an environment, and the environment has certain functions to update, and then it sends another signal with the state of the road. Additionally, there's something called a reward. That's the basis of reinforcement learning. That is basically a signal reinforcing a good action. So if you have good action, you receive positive rewards. If you have bad actions, or you don't receive rewards, or you receive negative rewards. I'm not going through details here. I just want you to understand that reinforcement learning deals with like the sequential decision making, deals with control, deals with taking actions in an environment. It's different than the other examples that I showed before. So basically, what I try to do here, what I try to do is to create like a kind of like a design tool, a design prototype for creating like floor plans for spatial synthesis that was like highly interactive. That's what this diagram at the bottom right is trying to show. Instead of like creating a generative model, change the input, look at the output, maybe look at the catalog of solutions, then changing the input again. I want something that's highly interactive, like something that where you have agents, they are constantly moving, and then you can actually go there, edit the agents, move the agents, and they will react to your actions. And that's where this is what I call an Academy of Spatial Agents. This is the first prototype where I trained like with 6 agents at first, later I trained with more agents. And I used reinforcement learning algorithms like DQN, DPO. And basically like each agent is, in this case, like a room. So you can see here, this is the program of a house, and each agent is representing a room, and they occupy this grid. And over time, they try to achieve certain goals in terms of shape, area, adjacencies, and so on. And as they're moving in the environment, you're generating like new floor plans. So that's the basic idea. So you have like this kind of like this simulation where your house starts growing and changing over time, what I think is like kind of like fascinating. And these are some examples of like stages of this floor plan over time generated by these agents. And then I just selected one here, and this is like a rendering of that example. And I think this is maybe one of the final slides. I'm just trying to show that what is really interesting about this type of like highly interactive models is that you could have potentially BIM or a CAD system that brings the intelligence to each element of your design. So in this case, we are developing like floor plans, but each room or each space has its own policy, has its own capacity to react to the environment and try to generate a floor plan. So here you have the designer interacting with those agents and trying to create a floor plan in real time. But I think that's the main goal, to have something that in real time you can change and the agents react, and you end up exploring like different interesting floor plans. Yeah, so I think I'll stop here. I mean, I think there are some questions that I can introduce here, like they're related to these projects, related to these topics. Like I'll just briefly read some of them. Like how can we design in face of increasing automation? How we can bring data and evidence to design practices? How can we understand creativity with machine learning models? And also from a more like pragmatic questions, what are the emerging design jobs and opportunities as the profession is changing, as technology, design technology is changing, and the role of architects uh, is also changing. And I'll stop here. Like maybe we can open for discussion if we have time, or I can also answer questions.
Amazing presentation, Pedro. Like
Okay.
I think there are one or two projects I saw for the first time, so it's like quite amazing, great work. And I'm opening this floor for everyone to ask questions, and even if like on the project, or if you have any idea which you wanted to develop with uh, deep learning and you wanted Pedro's perspective, or if you have taken inspiration from any of his model, we could also discuss briefly.
Yeah, I'm reading some comments. I think Ricardo mentions that Chair Gan was my first AI model. I'm sure if this was part of a workshop or was your own project.
It was my own project.
Nice. Using style
How
again.
I can see from your experience, like you know how to deal with many tools, right? With Unity, with Grasshopper, maybe with Python. How would you describe like your learning everything you learned, right? How would you what kind of tools should do we like get started, or what would you recommend for people who are like starting to get in touch with these new tools and etc.
Yeah, I think in the interview, my right talked a little bit about this, but I think my recommendation, what I really like about generative systems, is that it's a topic that it requires you like the basic tools, the ones that you're asking about. So I think today, if you're interested in deep learning, you should know how to code for sure. You should know at least the basics of coding if you want to develop projects, not only use like websites that they have models, but if you want to develop your own projects in research. Uh, and now at least like the standard language, I'll say it's Python. Of course, you can use like maybe C++ too, but in general, I recommend people to know a little bit of Python, maybe basic Python, intermediate Python, learn about some frameworks, libraries for machine learning and adjacent areas that are particularly like PyTorch. I think that's one that's very accessible and easy to use. And outside of the scripting, programming world, and machine learning, I mean, there are many libraries. If you think about computer vision, Python provides you access to a lot of libraries in all fields related to generative design. But outside of that, I mean, I think Grasshopper is a standard tool for architects today. That's the necessary. I really like Unity, especially if you're interested in interaction. Like there are a lot of things, if you're interested in event-based programming, I I found a lot of limitations in Grasshopper. Like Grasshopper relies on this graph that the information flows from left to right. So if you want to code interaction, you really need to to go like under the hood and try to change a lot of things in Rhino and Grasshopper. What I like about Unity that provides you all the workflow for you to create like an interactive environment. So if you're interested in have like really interactive environments with agents, I think Unity is a choice. And of course, if you're interested in animation, maybe you learn like Blender, Houdini, there are other software. But in my case, I'm focusing now on like machine learning. So in my case, I'll describe it as like Rhino, Grasshopper, um, potentially Dynamo, Beam, but I'm focusing on Grasshopper, Rhino, Unity, Python, and machine learning. This will be like my basic for my current research. Yeah.
All right, nice.
Fabio, you have a question? Maybe I
think
can't
he's
hear you.
mute. I think your sound.
Yeah, you probably need to press the
Your
button
mic
there.
might be off.
Maybe a different speaker.
You can type, I mean, if it's
Meanwhile, if you can write your question, that would be great. Thanks. Pedro, if you can share what are some algorithms of human machine interaction, like there are many out there for generative design. What are some which you find quite surprising or interesting?
human machine interaction. Yeah, to be honest, I think there's a very open field, because when you take like most of the examples that you have like with generative models, researchers invested a lot in visualization. So you have like, you create a model in Grasshopper to generate like maybe an office space, and then use an optimization, and then generate a catalog of options. And then you use like visualization tools like dimensionality reduction, like self-organizing maps, or maybe like Disney, you have some algorithms that take like maybe have thousands of options, but you want to organize them in a certain way that's recognizable, that you have like similar designs closer. So instead of having like this catalog of thousands of solutions, maybe you can start grouping them. You can use like a machine learning model to group them based on characteristics. So there's a lot of research on that part of visualization. And I think right now, recently, now there's more research on the interaction, like, because as I mentioned in the past, people say, okay, press play, run this model. Now I have like this catalog, or maybe now I have this algorithm trying to find an optimal solution. And after that, you look at the result and you say, all right, if I like it, I'll get it and I'll develop. If I don't like it, maybe I'll change my parameters and run again. But I think the challenge now as a researcher is like, how can you get inside there as a user and change the algorithm while it's generating the alternatives, right? So that's why I'm not sure if I have an answer, like what are the algorithms for human-computer interaction. What I've been trying to do is to get like conventional, let's say CAD interactions, like grabbing, moving things that you do like in conventional CAD modeling, and associating with reinforcement learning. So you have a model of agents, you can just grab one of these agents, move around, and that just send a signal to the machine learning model saying, okay, now the agent's in this different position, what this agent should do. Because reinforcement learning allows you to learn like step by step, so it's very like low granular, so allows you to create like conventional interactions, which I think is fascinating to combine with generative models.
I see. Fabio, is your mic working now? If not,
Oh, yeah.
I'll just.
I think he typed the question.
So the question is from Fabio, how the data sets are chosen? Is there any quality filter for the data?
Human design, and spread urban path select could be filtered by function. Yes. Yes, I think there are many ways you can filter, and I think that's like one of the roles of the designer in this workflow is to say, as a designer, the reason you're using like a data set, usually like data set can bring a lot of information about the design that's very intuitive. So you don't have like, sometimes hard to find a metric and say, okay, this design is optimal, this is not. Sometimes you just like the characteristics, right? So that's one of the good things about using data set. In that case, the designer can either select based on, one thing you can do is you take the data set and you use an algorithm, as I mentioned before, maybe like clusterization or like clustering, or dimensionality reduction. So use machine learning to start like creating clusters, and that's going to create like urban types. You're going to say, okay, I have a urban type with this type of maybe larger footprints, smaller roads, or maybe another one with like more like symmetric road system. So you can use clustering to organize that, and that helps you curate your data set. That's one thing. A second one you can use, as you mentioned, you can use metrics. So you can basically like organize the data set based on metrics. And a third one, as you can kind of like synthesize the data set. In our case, we didn't take like the cat drawings, we augmented, we added colors, we added like, it's more like creating like a cat drawing, but we based on data. So you can actually say, okay, maybe you can add the height of the buildings, maybe you can add isovis, maybe you can add environmental information on that diagram. So you're telling your machine learning model like what's part of that data. So this is one way that you can, another way you can do that.
We can take one more question from Harish, if you want to ask, or I can just speak it out.
In comparison with other models used for architectural design, what makes reinforcement learning models different? Because they use multiple agents, how do we train them? And do we start with certain data sets, or do we start with the agents and go on with the rewarding? I think like reinforcement, in my case, I used like a specific area that's multi-agent reinforcement learning. But I think what's specific about reinforcement learning is not the fact that you can use multi-agent. Let's think about one agent. I think reinforcement learning is useful when you have a problem that you're interested in a sequential decision process. So for example, if you're generating a floor plan, you just want to see the floor plan, you're not interested in how that floor plan is built, maybe you don't need reinforcement learning. You just like use again or another model, learn from data set, generate it. But in some cases, maybe you want to build that model. We want to have an agent that learns how to build that model from zero. There's an example, I don't remember now the authors, but a recent research on reinforcement learning when they taught like to use like basic cuboids, and the agent starts to stretch the cuboids, do certain operations to create like an airplane, to create a chair. So you're training like the process, you're training like a sequential decision process. So if you have a problem that you want to learn like for any possible configuration, not any, but like for a certain configuration of the environment, you want to learn that single action to create that chain of actions. If something that you can think as a sequential decision process, then reinforcement learning is the way to go. And for your second part of your questions, you're asking about data sets. Reinforcement learning is a very large field. There are like parts of reinforcement learning where you can work with data sets when you work in the offline setting. But typically in reinforcement learning, you don't use a data set. What you do, you have a simulation. Think about a robot. Maybe you have a simulation of a robot trying to reach an object, and the object, at every simulation, the object is in a different position. Maybe there are obstacles there. So you simulate that once the robot tries to do something, and that generates data. You simulate again the object, maybe the robot gets a little bit smarter, goes around the object and touches the target. So running that simulation multiple times generates the experience, generates the data for reinforcement learning. So in some cases, you don't need data. You can basically need to create an environment and a simulation that will generate the data from reinforcement learning.
All right. Thanks a lot. It was amazing
Thank you.
presentation, and I really like the discussion. Thanks for asking questions. We'll hope to see more work, and we'll follow your work on your website. Okay, so
do you want to share his website? Amir, do you want to share his website either on the Discord or on chat, just like people?
Yep. On the chat, maybe I can just share screen. It's Cradle Group, and yeah. The best part is like when I was going through their work, they have done research in very different areas, like all the members, like in NLP, in vision, reinforcement learning. So it's good to see those diverse kind of research work. Cool. All right. So we'll take. I will need to stop this live stream. We'll take 2 minutes break, and we have another presentation.